Hi, and welcome to Algebra 2 Honors Summer School, Day 12 of 16. Two-thirds of the way there. We're almost there. We have one more week of this, and that's good. We're going to be talking today about polynomial functions, and specifically about graphing polynomial functions. We'll do more of polynomial functions tomorrow, and their behaviors and ways to describe them and specifics. But today it's all about graphing. And we've looked at polynomials before. This particular one in red is a trinomial. There's three terms. Terms are separated by a plus or a minus sign. And these are in one variable, since there's only r is the only variable in this. The degree of the polynomial is the greatest exponent of its variables. So in this one, it's 2. The leading coefficient is the coefficient or the number next to the variable with the highest degree. So in this one, it's 4. And you will be asked to state the degree, the leading coefficient, and of polynomials when they're in one variable. If it's not a polynomial in one variable, you have to explain why. So in this first one, we have a degree of 4 and a leading coefficient of 7. The second one is not a polynomial in one variable. It's got 2 variables. Third one is not a polynomial. You cannot write 1 over x as x to the n power, where n is a non-negative integer. And that is what has to be true for it to be a polynomial. This third one, if we rewrote it in order, you would see that the degree is 5 and the leading coefficient is 4. So you're going to be asked to write a polynomial function using function notation, where we use x as the input and y is the f of x is the output. And x could be a number, or it could be a variable, or an expression like a plus 1. And we'll do some examples of that here in a little bit. What does it look like when we graph it? Well, if n is the degree, then n is the maximum number of times that this could cross the x-axis. Notice this has a degree of 3. This is a cubic equation, and it only crosses once. That's because the b value is above the x-axis. But it could go down below it, and it would cross it 3 times maximum, because that is the degree of this. Relative maxima and minima are turning points. And the maximum number of turning points that you can have is whatever the degree is minus 1. Notice here we have 2 turning points, one at A and one at B. The relative minimum is at B, relative maximum is at A. It's not the maximum because this goes up to eternity, but where it turns is a relative maxima and minimum. If it turns on the x-axis, this is called a double root, or it's 2 roots with the same value. That is, if it turns on the x-axis. Notice that this graph, after A, it crosses the x-axis once, but it's not a turning point. If B, the turning point, were on the x-axis, this would be a double root. And so you could actually have what is the equivalent of 3 roots, but it's only 2 actual different numbers, because the one is a double root. So watch out for this word double root. And the third thing is that the degree and the leading coefficient determine what the end behaviors is. And let's talk about that end behavior. But first, notice how we have a constant degree of 0. It's going to be a flat line that is horizontal. If it's a degree of 1, it's going to be a line, so it could be going up or down. If it's a degree of 2, it's going to be a parabola. This is like your x squared. A degree of 3 is a cubic equation, a quartic equation, a quintic equation. And notice how these all start where they start from. If it's a degree 3, it starts on the end behavior of each of these is a positive infinity, except for the first one, where it's a degree of 0. The end behavior, it's always ending at positive infinity. If it's a degree 2 or an even one, it starts at positive infinity and ends at positive infinity. If it's a degree 3, it'll start at a negative infinity and go to a positive, or degree 5 if it's an odd one. And let me just show you this next slide. So there's a line, there's a parabola. This goes to plus infinity. If A is positive, then it goes to plus infinity. It ends at plus infinity. And if it's a degree 4, again, the maximum number of turns you could have is 3. So we have 1, 2, 3 turns. Degree 5, the maximum number of turns is 4. What have I got here? If it's even, it's going to start at the top and go up to the top. It's going to start at positive infinity and go to positive infinity. If it's odd, it's going to start at negative infinity and go up to positive infinity. If my leading coefficient is negative, then it's going to be just the opposite. We're going to start at negative infinity and end at negative infinity if it's in, or it's going to start at positive infinity and end at negative infinity if it's on. So we'll watch that. And here's what it looks like. So this is something for you to pay attention to. It's an even degree, so it starts and ends both in the same direction. And it's going to be, the coefficient is positive, so it's going to be up and up. And the end behavior is going to end at a positive infinity. For an odd one, it's the positive leading coefficient, so it starts at a negative infinity and ends at a positive infinity. And here we have a negative coefficient, so it's going to start negative and end at negative. And for the odd one, it'll start at a positive, and the end behavior is it ends at a negative infinity. Okay. Location principle. The location principle, let's see an example. Let's look at an example of this. Location says that the principle says if you have a function, f of x, and two numbers, a and b, where the f of a is greater than 0 and f of b is less than 0, then the function has at least one real 0 between a and b. Now, this is a lot of words, and it doesn't mean much until we put it to action. So let's look at an example, then you'll understand. So here's an example where I have the graph of, you're supposed to graph this function, x to the 4th, x plus x cubed minus 4x squared minus 4x. The leading coefficient is 1. From this, we know that it's going to have an end behavior of a positive infinity. It's going to go up at the end. That's because it's a positive number, greater than 0. The degree is 4, so it's going to have 3 turning points. It means the maximum number of times it could cross the x-axis is 4, and it could have turning points, or it could be, let's see, and it's going to start at a positive infinity because it's even. So it could look like this, or it could look like this. I don't know. In this example, I would have 2 real roots and 2 that are not real, 2 that are imaginary. The turning points are above the x-axis. It could look like this, where I have 1 turning point on the x-axis. That's called a double root. That's where you have a turning point is on the x-axis. That means that 2 of the roots have the same number. But they're 2 separate roots because it's a turning point, but it's as opposed to just crossing the x-axis once. You'll see this as we get through it. Double root. So let's look at this. One way of doing this would you could make a plot of it. You could make a table of values and plot the points and then smooth the curve. Now, according to, if we used to have to do this by hand, and I think that that's why these books and these textbooks that we have you doing this and talk about this thing called the location principle. In the old days, we had to do all this by hand. And so the location principle says that if you have 2 values for x and one is positive and one is negative, like here we have x of -2, it's a positive number, and x of -1 is a positive number. That means that you have to have at least one real root in between them, and that's going to be at -2. So this is one way of finding the roots. Another way that you could do this is you could plug this into your graphing calculator. And I tell you this because some of you are going to take the SAT or ACT test and you're required a calculator, and they don't let you use Desmos, at least not today. And maybe they won't even require it after COVID. Maybe they won't. I've heard talk about them, some colleges not requiring you to take the SAT or ACT anymore. Anyway, one way to do this is to graph this other functions. So it has to be y in the form y equals. And then you're going to select the calc button, and you either select a minimum or a maximum. Use the keys to give a left boundary or right boundary, and then do the other boundary, the left boundary, and then the right boundary, and then it'll tell you what the root is. So if you wanted to know a second root, you'd have to go over further to a different way, and you can see it on your graph when you graph it on a calculator. But better still, and this is way cool, this is with Desmos, you plug it into the Desmos Calculator and you click on the graph itself and it will show these points. Now, I've also clicked on the points individually so that they would stay lit up and stay to where you could see them. But here we can see that these points are the points. These ones down at the bottom here are the turning point, are the zeros or the roots. And these other ones are the maximum, relative maximum, and relative minimum. And there's two of them minimum. There's one down at the bottom. So in the practice problems, and that's what I'm going to do now, you're supposed to state the degree, the leading coefficient of each polynomial, and tell me if it's a polynomial one variable, and if not, explain why not. So here we have the degree is 4, and the leading coefficient is 6. No big deal. The second one, I'm going to multiply this out so that I can write it as a polynomial, not as a factored polynomial, as an unfactored polynomial. So I'll expand it. So this is the same as a cubed plus a squared minus 4a minus 4. My degree is 3, and my leading coefficient is 1. From the leading coefficient and the degree, I immediately know how to graph it, something about what the graph would look like. Here, p is 4, so when we substitute 4 in for the values, we get 4 squared minus 3 times 4 times plus 8, which is equal to 12. If I plug in a -2, we do the same thing, and I'm putting it in parentheses what I'm plugging into this equation. I'm working it out really quickly, and I end up with 18. But I said before that the x value, or the thing, the f of x, the function could be a function of a variable or a number or an expression. And that's what we've got here is two expressions. So the first one, I'll plug in 2a cubed into my equation, and then I'll simplify it. And I'm going to do the expand what's in the parentheses first, and then I'm going to multiply it out. So I get 12a to the 6th minus 4a cubed plus 5, and that's my answer. In the second one, we have 2 times this polynomial, and there's the expression on the inside. So I'm going to write this as 2 times, and I'll plug in x plus 4 into the equation for p. I think on some of the questions it had to use r. We didn't use r in this particular one, these two, so you can use r in the other ones that you want to try. I'll expand this. You can use the box if you want to expand this. I'm just going to expand it like this. And then we have 2 times 3x. I combine the like terms. Notice you have a 24x and a minus 2x. And here we have 48 minus 8 plus 5. Simplify this once again to get my 22x and my plus 45. And this is equal to 6x squared plus 66x plus 90. That's my answer. Describe the end behavior. Here we're going to negative infinity, positive infinity, and positive infinity. If it's going to positive infinity, I know that at the end behavior, I know that my leading coefficient is going to be positive. It says determine whether it represents an odd degree or an even degree. Here we're starting at negative infinity and ending at negative infinity, so this is going to be an even. Starting at a positive, ending at a positive, it's an even. Starting at a negative infinity, ending at a positive infinity, this is an odd degree polynomial. I am supposed to state the number of zeros. Oh, first of all, let's see. This has 4 root. This has, what is this? The degree of the polynomial. This is a 4-degree polynomial, at least 4, and this would be at least 3. It could be more, but I'm just going to say it's 3, 4. The leading coefficient here is going to be negative, and this will be positive, and this last will be positive. It didn't ask for that, but I thought it'd be good to show you. Here we have no real roots. See, it does not cross the x-axis. In the second one, I'm going to have 4 real roots. You can count them. It's a 4th-degree polynomial. The maximum number that I could have is 4, and I do have 4. In this last one, I have 1 real root. I could have 3, but I don't. I only have 1. It only crosses the x-axis once. Also, I'm going to look at the turning points just to show you that this is something that we talked about. This one has 3 turning points. It's a 4th-degree polynomial. The most it could have is 4 minus 1, which is 3. This is 3. It's 4 minus 1 is 3. This is 2. It's 3 minus 1. It has a turning point here and here. All right. Plot your answer in Desmos. List the zeros and maximum and minimum based on the Desmos graph. Oh, how easy is this? This is so cool. Here we go. You plug it in, and there it is. You click on the graph, and it'll tell you the zeros, and it'll tell you the maxima and the minima. Okay. And the last thing we're going to do is sketch a graph that has the following characteristic. It's got an even degree polynomial, 4 maxima, and 3 minimum. That means this is going to be fourth degree. It's going to start, either it starts at the top and ends at the top, or it starts at the bottom and ends at the bottom. If I only have 3 minimum, that's going to look something like this. And I'm not sure where I'm going to put the x-axis. It doesn't say. If I did here, I would have 1, 2, 3, 4 maximum, and 1, 2, 3 minimum, relative minimum, and I would end up with 1, 2, 3, 4, 5, 6, 7, 8 possible roots. And that's all there is to it. Real roots in this particular instance. At most. There we go, at most. So good luck and success.